There is this Fluske something, some book, advanced condensed matter students follow. I'll check out the exact name of the book. Then there is another book I personally like a lot. It's a Altland Simmons, many body physics, or quantum field theory for many body physics, something like Altland Simmons. So any book on many body physics should have second quantization, but Feynman is supposed to be the easiest because Feynman is usually the likes have a very heuristic approach to anything.
But the book you said that does not contain properly second quantization. I mean, I couldn't find second quantization in the index or Fox space or something.
Which book? Feynman's statement,
Yeah,
set of lecture.
yeah. No, not set of. Yeah, I think that book you mentioned in the lecture.
Yeah, the book is called Statistical Mechanics something. Feynman's
Yeah, yeah,
Statistical Mechanics book. I
yeah.
think chapter 6 is entirely on second quantization.
Okay.
Yeah.
And the MIT coursework is completely technical. It does not contain that much physical insight. It's like the
Yeah,
formalism
yeah.
and all.
Yeah. So you will not find an exact replica of what I am doing, right? I mean, then it is like then what is the point of coming to class? Then you can read everything from book. I have my own way of doing things. So don't expect what I say exactly to find it in a book. First of all, it is not from a book. It is from a bunch of books and my own experience of how I look at things. And secondly, it is there is no single book you will find things in a topic by topic analysis, right? Just this order I say it. But I suggest one book where you find everything in one way or the other, at least all the important things, and that book is Statistical Mechanics book of Feynman. Okay?
Okay, sir.
But if you expect that there will be a place where everything is written in exactly the way I said it, that doesn't exist. Maybe it will exist when I get old and write a book, but not now.
Okay.
Okay. Okay. So, but if you need some short note or yeah, I don't think I have written the notes in a coherent way either. But Feynman's chapter 6 of statistical mechanics book is good enough. Actually, I had some. No, I don't have it. It is some other note. Yeah. So I cannot send you the book because it is not legal, but I can tell you exactly which page number, etc. Okay. Okay, so let's do a quick summary of all the things which we discussed earlier on identical particles in quantum mechanics. All the important points. So we started with by stating that the Schrodinger, we wanted to solve the Schrodinger equation of identical particles. And we said that equation is following. So this part, up to this part, it was very familiar to you, but then I said there will be other 3-body, 4-body, n-body terms, depending on various contexts. So this is the equation I wanted to solve that. And we noted that the way of all the forces we know, or all the potential form we know, that means that implies that the Hamiltonian has a permutation symmetry. So that implies a restriction. So asymmetry always means a constant, a restriction. Okay. So this implies a restriction on the allowed symmetry of wave function. Although there is no reason a priori that why the wave function should follow this exact strategy, and that is where the postulate comes in. So then the postulate came in. Which is commensurate to observations in 3D. We skip the 2D and 1D case because it's complicated in 1D to think of exchange without interaction, and we are avoiding interaction in this course. And in 2D, it allows another extra factor of arbitrary angle, phase angle dependence because of exchange. So we are focusing mainly on 3D or those part of 2D where there are only two possibilities. So this leads to two type of objects. One is a bosonic, another is fermionic. By the way, did anyone else had problem to find this chapter in Feynman? Others found this chapter?
Sir, I have found that
Sir,
in chapter 6 there is a thorough explanation. Thank you.
Okay. And others, did you find this? Someone else?
yes, sir. The notes that you have
That-
linked here, that does not have the full agenda properly. But I guess then the chapter has that.
So where it doesn't have, you said the book doesn't have it fully, or?
No, the link that you posted on Piazza doesn't have the full agenda.
Link means the MIT link, right? Your voice is choppy, I don't hear it properly.
Yes.
So the MIT link doesn't have everything, it has part of it, and part of it is there in Feynman. But if you read those both, these two things together, that is enough to know everything I am telling you, okay? And that is enough to prepare you to solve any problem. I will also discuss some examples. And there are some examples in all these books you read, like Jet Li and all that you can look up there. But I will also discuss some more examples. Already I did, but I will do some more. Okay. So bosonic, the word bosonic is reserved for a n particle wave function, which is fully symmetric under pair permutation, and this is for antisymmetric under pair permutation. This is what we learned so far. So then we discussed the n particle wave function. We wrote it in terms of one particle wave functions in terms of wave function, and in general such options are psi, Li, Ri, if they are distinguishable. In general means distinguishable, where these are single particle wave function and this is the n particle wave function. And this number tells you the set of levels occupied. These are the eigenvalues of the, and these are, in other words, eigenvalues of single particle levels. Good quantum numbers. Single particle Schrodinger equation, single particle Hamiltonian. Okay. Then we constructed the symmetric wave function, and we said instead of using the labels, we can also describe it using the labels, because we saw there are two ways to describe it. It is best to describe it in terms of the occupancy of levels. So this contains the same information as this, but in a compressed form. So instead we wrote it like that, and we say n1 factorial, n2 factorial, n infinity factorial, n factorial, and the permanent permanent means I write it as sum over all the permutation of this object. Which you can write it in this determinant form in a matrix form and take the permanent. So this is permanent of this matrix whose entries are given by phi li rj. Then we discussed, so now if I tell you that let's say there are a certain number of fermions or bosons in a particle in a box or particle in an oscillator, in a single harmonic oscillator, then you should be able to write down its many body wave function because you know the single particle wave function. Similarly, I can write this. All you need to know is the occupancy information or the Li, or which particle is in which Li. This is an alternative way to write this, and this is nothing but which is nothing but the determinant of this matrix. This is what we have learned so far and did examples, etc. So now let's move on and talk about the other further on this, that what description we developed for this. So this basically completes the whole picture, but we went further and introduced something called a Fock space. Notice that Fock space is nothing but this space, which space of wave function which are in sync with symmetrization postulate. And there is a nice way of writing this Fock space. So Fock space is completely specified by this number for any arbitrary number of particle, and this is nothing but the occupancy information n or n infinity, whatever you have. And we developed a language to do that. So the other way of writing it is this psi nk, symmetric or antisymmetric, or this. These two contains almost the same information, except the fact when you write this, you also write the explicit form. You have a room to write the explicit form of the wave function. So actually, if you need the wave function, so you can do, generally this is a very useful picture to do many calculations, and at the end you always commute back to this picture and put your wave function information and write down the full wave function if you need that for some purpose. So in many problems you don't need that. You don't need it immediately. You just need the information and energetics and calculating the energy levels and the spectroscope to do the spectroscopy, etc. But in some problem you need that. Let's say you are doing a problem in chemistry, you want to know what is the form of the orbital or the molecule shape, etc. Generally in few body quantum mechanics this is also useful. So then you can always commute back to this, and it is useful to know that how you can, which we did in last time, an example explicitly, how you can write an wave function, many body wave function this way, and go from one to another. Okay. So we found an alternative description when it is written like that, is using this A dagger and A operator, or F dagger and F operator. So we learned that if there is a pair of A dagger and A operator that follows, let's say it is some k prime, delta k prime, and other commutators are 0, and then it fits to describe a bosonic state, and you can write an arbitrary bosonic state in terms of like some arbitrary nk states by applying this. So let me write it in a schematic way. By applying this A dagger operator again and again, on a vacuum state which has no particle. Okay, it's just a schematic way. I'm not writing the full form. Well, you can, if you want, you can also write it. I forgot the factor, but it will be like some a k to the power n is nk starting from 0 with some appropriate normalization. And then we learned that if I have another operator, which is this, this is anti-commutator, and the relevant other anti-commutators are 0, then it is appropriate to describe a Hilbert space where nk can be only 0 or 1, or appropriate to describe Fock space where nk can be only 0 or 1. Okay, and then in a similar way you can write down that description also, and we did some examples on that. We showed that the algebra, how the algebra plays a very important role. So then we did this illustration of many particle, and we showed that if I have a scenario of 1, 1, 0 and I exchange these two particles, then according to Fermion, if it is fully antisymmetric wave function, you can write it in this psi form. It should pick up a minus sign. But instead, if I write the 1, 1, 0 in this way of writing, the 1, 1, 0 is nothing but, if I call it 1, 2, and 3, f3 dagger, f2 dagger, 0, 0 means 0, 0, 0. Then this already contains the information that if I exchange these two particles, and I showed some way to do that, that if I exchange these two particles, it will pick up a minus sign. The process will pick up a minus sign. So this way of writing already also have all the anti-symmetrized information because of the anti-commutator. And you can also check if it is bosonic, then it will not pick up a minus. Okay. So everybody is in the same page up to this.
Yes, sir.
So do we have a convention to write the lowest energy to the left or something? Like
No,
here you went with E21.
Yeah, either way is fine. And I showed you last time that whatever you choose, the only thing mattered is the relative minus sign. And when you do there is no rule. I mean, you can do either way, left to right, right to left. But once you pick a rule for a given problem, you have to stick to it. Otherwise, it will mess up, right? That's the only thing.
Yes, sir.
Okay. Anything else? So we will discuss two examples today. So my plan is following. We are running actually a bit slow, but let's see how much we can cover. So my plan is following. So today I will talk about one example for a. My voice breaking?
It's fine for me.
Okay, so it's probably a local internet problem. Okay, so what my plan is today is to further talk about some examples. So two example I plan to talk about today. Hopefully I'll be able to finish it. One is about a picture of many bosons. Okay, a many boson picture in terms of using this oscillator creation and annihilation. This is a so now this everything you need to know about many particle quantum mechanics is right here on this board. If you have internalized all these points, it's everything is already with you. Okay. Now we'll talk about some example and application of these ideas. So one example I do in terms of bosons using oscillators. One, and then I'll talk about this something called the exchange force, which involves I'll discuss two particle examples. And then in the next class, I will talk about a many fermion example, and then maybe some other further discussion I'll do, and then that will end this chapter. But there is a lot more interesting, so this chapter can become a whole course actually. It's almost true for any chapters, but this chapter it is especially true, because what I'm deliberately avoiding is interactions and how to write the wave function and Hamiltonian of an interacting system. That I'll not talk about in this course, but I'll refer you to some references, and you are encouraged to look at that. And then from Wednesday onwards, I'll move on to some new topic. Okay. So that is the plan.
Sir, can you switch
Yes.
off the light just above the board?
I'll do that.
Yeah, that's better.
Okay. So notice that we have learned about two type of quantization. So now let me tell a bit about the name. So always the names are not necessarily, as you have seen throughout quantum mechanics, there is always a struggle between the lack of vocabulary, lack of appropriate vocabulary, and what actually that represents. And that's because again, like English language is not developed, or any language is not developed for this kind of purpose. They are transactional purpose development. And then when you say something very weird, then due to lack of words, you use a word which is originally used for something else, and then creates a wrong picture. But that's how it is, and we have to deal with that. Like state is one classic example, spin another example, but that's the close enough word, so that's how we deal with it. So there we have encountered this whole phenomenon, this whole description of creation annihilation operator picture is called second quantization. But you might wonder, then what was the first? So there was, without a first quantization, how come a second came? So the first was, if you want to give a first, the first quantization is the fact that quantum mechanics suggests that everything is quantized, right? The energy levels are discrete and all that. So that is the meaning of first quantization. So it's, but for that you need to view a particle as wave. Particle as wave. But second quantization takes you from wave to particle. Because if you think crudely, what I'm visualizing a many-body wave function, a many-body wave function I'm visualizing is as if I'm adding particle, like going from one to another is like adding a particle. Okay. So this picture is called that is why it is a wave to particle picture. Although this particle is not the same as the original particle, but this is how you visualize the wave in terms of a particle. Now there is a little more depth into this statement. And that statement is associated with quantum field theory, because second quantization was developed and was a tool to go towards quantum field theory, where you visualize a field as also a particle. Like you can, and I will not go into this right now, and maybe in quantum field theory course you will go into that. And if you look at a little later in the course, you will see some attempt to quantize a field. An electromagnetic field will be written in terms of photons or in terms of this creation and annihilation operator. So that is an attempt to quantize a field, and that is where the term second quantization came from. So it's a second quantization. So let's do some examples which is associated with a particular type of photons, a particular type of bosons, which is phonon. So I'll come to a moment what is a phonon. By the way, any of you know what is phonon? Let me start with BSMS students. Did you you are taking a course on solid state physics? Have you encountered the term phonon?
Yes, sir.
Yes, sir.
Oh, very good. So you already know. And so how did you learn about phonon? You learned about it. You started with a bunch of coupled oscillator, a mass spring model, and then so it is like a bunch of these, like that, and then you Fourier transform it and convert into some independent oscillators. Okay, let's say some independent oscillator. And the excitation mode of these independent oscillators are phonon. Is this how you learned it? Okay, this is another thing I have noticed about your batch, which I don't know if that happened in previous batch. Some people have opted out from solid state physics. Now, it is generally true that your course structure is designed in a more liberal arts way, where you take whatever you like. But if you want to be in physics program, you have to give various, at least in India, you have to give various entrance exams like NET, GATE, JEST, right? And they have a particular syllabus. So don't drop any course from that syllabus. Solid state is a course from that syllabus. And even if you have freedom to choose whatever you want, don't mess with that unless you are totally sure you don't want to appear for those exams. So this is what I have seen more than one of you. I don't know why did you choose it like that. So be careful about this point. Okay, so others, do you know about this picture of phonon?
So we just went through the theory of elastic waves, not like this. And
Okay.
yes, sir, we were just introduced to like some vibrations to be quantized, and it was told that they are phonons.
So you went to a description of it, or you didn't derive it, or didn't do any calculation?
We derived for an elastic wave, like we consider like two different particles. Two like in a lattice, we have two atoms, and then M1, M2, and then they're all connected by a spring. So how will an
Oh,
elastic
you
wave
did it for
travel?
two atoms. Okay, that is also fine. So you have two mass coupled by a spring, and you went to their normal coordinate and quantized it. Is that how you did it?
Yes, sir. I guess that would be fitting.
Okay. Okay, very good. Now, what about others? IPSD and PhD. Are you familiar with phonons?
Yes, sir. We had a course in our bachelor's of introductory.
Okay, very good. So let me give a brief example, brief outline of how these phonons and like how these phonons come and how to describe them using this second quantization notation. Yeah. So, so there are these different kind of bosons you will encounter. So if you look at this problem I gave you in the assignment, in the third assignment, that's a problem of this rubidium atom. So the rubidium atom is a bosonic atom. There are not, you don't need to go to that complicated. Even helium can be in a bosonic state. So there could be this a particle bosons, a set of bosons, which could be this rubidium or helium ion or certain state. And you can think in terms of and when you have many such, you have box of gas of that kind of particles, then you can think it like and you cool it at very ultra low temperature, you will see all these bosonic features. Similarly, there can be fermionic atoms, etc. And then there is another category of bosons which comes as a excitation, okay, excitation of something. So that is what one category such is phonon, another is magnon, okay, and photon. Now photon is different because photon is a gauge boson. So you will know later what you know already what is a gauge theory, but photons has to follow certain gauge constant. So their description is a little complicated, and that leads to the whole formalism of quantum electrodynamics, which we will not do in this course, but probably we'll learn it in quantum field theory course. But if you want a big glimpse, you will see it in the there is some discussion on it in Sakurai. But the simplest of object of all this is phonon and this kind of isolated bosons. When we discussed this problem last time, we thought of them as these bosonic atoms. Like we discussed this problem where you are putting bosons in a particle in a box or n particle system. Okay, in a many state system where you are putting bosons, and I gave you some configuration like 2, 2, 3, something like that. So that time I had this kind of a thing in mind. But these are also very important example. So let's see this example. So earlier we have discussed this kind of thing in the context of a single particle. So what did we discuss at that time? So we discussed this in terms of a simple harmonic oscillator creation and annihilation. So there the role of boson was, role of this operator was to go from the states, apply a dagger, you go up, like that. Okay? And we wrote down the Hamiltonian as n plus half n. Okay. So a dagger creates a quanta of energy. So if you want to use the language of creation. So now we will use this picture in a many boson context. So context is phonon. So how to think about phonon? Let me quickly go over that. So let's say I have this bunch of particles, mass spring. Like that. And each particle does a small displacement. So these masses have, these springs have a constant K1, K2, K3. because of transition symmetry, I will assume they are all equal. K1 is equal to K2 equal to K3. And the masses are also equal. So I'm writing it like M1, M3, M4, but you will assume this are equal because there is a translation symmetry in the system. I assume a translation symmetry. Of course, when it is not there, then what happens? So who is this? Sri Lakshmi. So catch Sri Lakshmi to learn what happens when there is no translation symmetry. I think some other folks also know it, but they are probably not in touch of it, like Rukmini and some other Kartikeya. They all discussed with me that last semester what happens when this symmetry is not there. But let's assume this symmetry is there. Okay. So now the formal way to go to normal mode is basically you even if you have not learned solid state physics, you must have seen it in classical mechanics, is to do this Fourier transform. So A is the distance, a mean distance between 2 points, and J is their coordinate. Okay.
Sir, blur means the board is not visible.
Really, is it out of focus or something else?
It's
Internet
blur.
issue.
Yes, yes.
Is it visible now? Okay, it's
Not
an
yet.
internet.
Not
Is
no,
it
not.
uniformly blurred or it's blurred at a corner?
No, it's uniformly blurred.
Okay,
Uniformly
then it's a
blurred.
connection issue. Then it's a connection issue. Okay, this is what you get when you in board writing. That is why tablet writing is better, but somehow you prefer the board writing. Okay, so let me write it down here in this part.
Yeah, it's visible now.
Yeah, so this will go on. I don't see a solution because depending on the internet connection, time to time some people see it a little blurred. It's like watching this 144p YouTube videos. Okay, so now if you carry out this transformation, this Fourier transformation, and use these two things, that there is a periodicity, which means this mass and spring are on D. Okay. This is called periodic boundary condition. You will learn all this in solid state. I'm just giving you a glimpse of this. So don't worry if you don't understand all the. So I leave some steps here because you will actually learn it in solid state physics. And don't worry about it. I'm not going to directly ask you an exam or something. But I expect you to work it out in your hand once at least. Okay. So, and it will follow even if you're not following how to go from this step to that step right now, it is okay. But you should at least follow what I'm trying to do overall. So I can do this Fourier transform, apply the periodic boundary condition, use the quantization. So after a few steps of algebra, if you start with a Hamiltonian like this, so this is my original Hamiltonian, and let me write down my the original Hamiltonian. So the original Hamiltonian is H is equal to half pi square plus sum over I plus half nu xi minus xj square. So this is basically I'm telling you I, j when they are neighbors. It means there is a harmonic term. It's the oscillator term, which is a square of their distance, square of the displacement of the neighboring particle. So that is how you describe this. So this is your x1. This place is a bit congested. Let me draw it again. So this is your x1, this is your displacement x2. So this is the small oscillation form, and you write the whole Hamiltonian as sum of the momentum square plus sum of the displacement square. So this is the harmonic approximation. So then if you apply this set of transformation, the Fourier transform, you use this whole thing, you will land on this. Notice I have not yet used, so you don't need to use this yet. So it is still classical mechanics. It is just going to Fourier space. Now if you impose this, that
Sir?
pk dagger, yes,
Sir, what p minus k and x minus k indicates, means that suffix?
yeah, it is just momentum with a negative sign.
Okay.
It comes from the identity of delta function using Fourier transformation. Are you familiar with that identity? If you Fourier transform a delta function, do you know how to do that in discrete space?
Yeah.
Okay, so it comes from that. And furthermore, this pk is p minus k. Why? Because if you look at there, if you here should be pk. If you inverse Fourier transform it, when you flip the sign of k, the pk dagger will become minus k, and that also is equivalent. So either you make k to minus k or take k dagger. Both of them are same thing. So if you use this thing become pk dagger, or you can write it in a flipped way, xk dagger. Okay. And then you apply your second quantization, which means you write a is m omega k by 2h bar okay, and a dagger is correspondingly dagger. So then you rewrite this Hamiltonian as this. So what happened in this whole process is that you started with a set of coupled mass with spring, and then you landed on a equation which is a bunch of independent oscillator. So your starting point is this and your end point is this, right? This is your end point. So what is phonon then? So phonon is the occupancy of this many particle state. So what is the ground state of this many particle state? Yeah, what will be the ground state? So you can call the ground state as the no phonon state. Okay. So let me rewrite that. So let me take this Hamiltonian and write its full eigenspace. Okay. So the H eigenspace is where alpha is this index. Okay, and this is nothing but product okay. So this problem, the ground state is the eigenstates are given by some occupancy with this eigenvalue, okay, because you know if you put n particle in n state, then that means in alpha state, that means it will get an energy of n alpha plus half, and the h cut omega alpha with n1 n2 whatever is the occupancy of that, and you can construct this state starting from vacuum by applying the creation operation again and again. Okay, so do you follow this? So you may not have followed because I have not showed it explicitly, but do you understand that how starting from here in principle I can reach here, and how from here in principle how I can reach here, and once I reach here, then you are totally familiar with this problem in terms of this second quantization language. Okay. So what is phonon? So phonon is, so what is this ES for? You understood everything or it is for blur? No comment. Okay, what about others? Are you following this?
Yes.
Yes,
Okay.
sir.
Okay, so phonons are basically this set. Okay, so you can say call this set as 0. When there is no phonon, then this is 0 0 0, and then when you add on, then they are basically first state, second state, third state. Okay, now notice that this is, so what is physically happening? So do anybody understand the physical significance of this Fourier transform? Why do you need it? Why do you do it in solid state physics or anywhere else? I know you do it for going to normal coordinate and all, but where are these modes located physically? Where are these particles actually? These phonons.
The reciprocal space.
Very good. So what is reciprocal space? Why do you need that? I know that you have spent a lot of time doing reciprocal space perhaps, but why do you need that? Can you tell me one realistic example from experimental, from a practical point of view, that why do you care
To
about
do
this?
things frequency-wise.
So X-ray
Diffraction
diffraction.
experiments.
X-ray diffraction frequency wise, I had two answers. So why do you need to think of X-ray diffraction when you think about, why do you need to think of reciprocal space when you are doing some diffraction experiment? What do they represent? Why can't you deal with it in real space?
Sir, because like the spectrum of that experiment will have inverse properties, right? So if the lattice space points are closer, the results of the spectrum of the diffraction, the spots will be further away. So you need to.
No, you are saying what do they mean? But I'm saying why do you need that even? That is a different question. I understand that you know what it is, but why do you need in any problem to go in the case space and analyze this case space? Is it a mere mathematical convenience or it's something more? Okay.
In
So-
X-ray diffraction,
Sir,
it's difficult to check all the parallel planes.
All the,
So all the parallel planes.
what is parallel
How-
frame?
Sir, are you talking about solid state or whole? Like, why do we do
means
that at all in
No,
any
it
branch of
doesn't matter
physics?
what you call it in any subject.
means
Okay?
Rohit want to say by representing HKL, we are presenting a set of parallel planes. Means by
What is parallel frame?
indicating,
What is,
means
I didn't get
when
this
I
point.
introduce HKL, it represents the whole set of planes directed in that particular direction. When I represent that HKL, so by doing that, the size of the problem reduces.
Okay, so
Wants
you
to
think
say.
it's more like a convenience.
And one more thing is when we do the diffraction experiment, the slit it depends on the slit width. So the width of the slit is the measurable quantity that is that in real space. But when the diffraction pattern occurs, how they are related, for that we must have to introduce that that
No, you
Fourier
don't have
transform.
to. You
So
do it
Sir,
for convenience. Yeah.
I think we want to check how things occur for a particular frequency, and if we plot that and somehow we trigger the system with an outer frequency, then we will see how the system is interacting. So in this way, if we go to a reciprocal space, like if we go to the frequency space, so it will help us to know what is happening to the system for frequency wise.
Yeah, so this is towards the correct direction, but not yet complete. So let me try to answer you that why do you need even anything of that sort? So think of the main reason you need it, because it's a collective system. It's not an isolated system. It's a connected system. So think of this example. So let's say if I hit an object, right? If I hit this object with something, right? So if I hit this object with something, it will produce a sound. Okay. Now that sound is, if it is metallic, it is more prominent, but it is plastic, so it's a little. So if I hit it here, no sound, but if I hit it here, there is a sound, and that sound causes a vibration which I feel here non-locally. Okay. So that means you cannot think even this problem as a one particle in isolation, because they are coupled. These particles are coupled. That's why, so you cannot think. So when a excitation is given, it doesn't excite a single guy. Okay, it excites all the particles collectively in some way. So this collective excitation, to describe that, you need to go to K-space, and it is true for anything, any experiment you do. Let's say you hit an object, you hear the sound. That's an experiment, right? It's a perturbation which you hear. X-ray diffraction, you hit the object with X-ray and you hear the response, or you capture the response in some detector. So in all these experiments, the actual phenomena is happening in K-space because it's a collective phenomena. Okay. So this is the physical reason why you need to do all this K-space business. And then of course there is a convenience point of view also. But it is also because there is nothing happening in isolation. It's not you are exciting one particle. Now when you say that I am exciting this phonon mode, which means the particle is in this excitation level, that excitation level, or something. So let's go to the phonon later. Let's think classically. So even in this picture, when you write down the thing in terms of this isolated, when you go to normal modes, what are you doing actually? The normal mode is basically you are starting with a coupled problem and doing some transformation and converting this problem into an isolated oscillator, isolated coupling. But where are those oscillators located physically? They are physically located non-locally over the whole system, right? So these K modes are basically this kind of modes in the whole particle, when the particles are located like this. So if it is this kind of vibration, it is like that, and if it is this kind of fluctuation, then it implies, this mode implies just how much it is oscillating. So when you say I am exciting a single K mode, that means that you have excited the particle in that particular, in real space they are oscillating in that particular way. Okay, this is also true for X-ray diffraction and everything, and that is the information you are capturing. Okay, so now when I say that I have these excitations, it means that I have excited the particle in that, and the quanta of that is phonon. Okay? So that many phonons I need to excite it there. Is the picture clear? Okay, now one more point is, in real world nothing is harmonic. Okay, which means there are terms like that, which is some arbitrary power. So then you cannot play this game. Then when you come here, it is not interact like this. It will have addition of three phonon, 4 phonon terms. And then you can never isolate a single mode. Then it becomes a coupled and interacting problem, and that is what most problems are. Okay? That is what most physical problems are. And they are very non-trivial, but one can do approximation and use perturbation theory, which you'll learn later. But this is roughly the physical picture of this. Now one more step is that in this problem, generally it is written by taking the zero mode energy, the 0 point energy, by setting that as the ground state or the total zero. So you can write this problem as h cut omega k ak dagger ak, simply ak dagger ak, and you assume that this whole so the ground state energy is now infinity, because it's sum of h cut omega k by 2 over all the modes, over infinite modes. And then the rest of the problem is, everything is same except these halves are gone. Okay, this is another alternating way to write it, and that tells you, then you visualize this whole problem. No phonon means zero energy, and then when you add phonons, then they are getting in higher and higher energy state. And you can describe these phonon energies as simply n1 h cut omega 1 plus n2 h cut omega 2, like that. So if I give you a particular configuration, you immediately know the energy and everything else. Okay. So now is everything clear so far? Everything, I didn't, of course, describe it as a technical calculation, but are you following that what is the meaning of a normal mode? Why do you need to go to reciprocal space at all in any problem? And why they are physically significant? And where these AK modes are actually located. These AK modes are excitation of these which are actually non-local, because we know K space, something local in K space means it's non-local in real space. Are you following everything?
So I have a doubt on how you wrote the Hamiltonian in the second step. Like,
Yes.
so usually in the case we have like two adjacent particles like xi and xi minus 1
This
interacting.
step, you mean to say this step?
Yes, sir. Like,
Yes,
sir?
tell me.
So in
Yeah.
the second step, you have only considered xk, like not the xk minus 1 and xk plus 1 particles, writing the Hamiltonian's potential energy. So are we assuming that the two nearby particles don't interact?
No, this is the whole point of normal mode, right? You start, if they are harmonic, you can do a transformation and go to this point where everything is non-interacting. Right? That's what will happen when you do the Fourier transform. Are you familiar with this exercise or not?
So like I don't understand how like Fourier transform helps over here.
Okay, so it's not alone the Fourier transform. You first have to do the normal mode, then the Fourier transform, or you have to first do the Fourier transform, then the normal mode. One of the two. But this isolated oscillator picture is from normal mode. It doesn't require any quantum mechanics. It's just a classical picture. Do you follow this now?
You mean like writing down the Hamiltonian like that? Like
Yeah.
for an isolated, yes sir.
So you first start with a coupled. So think of two particles. Don't go to n particle. Don't go to Fourier transform. Take two particles, transform it into normal modes, and then go to the AK dagger AK business. Then you get two isolated oscillator, right? Following?
Yes, I don't understand you there.
No, you don't understand this two particle example.
Yes sir, like how Fourier transform helps. Like I can
No,
Fourier transform it.
first did you understand the two particle example? That in the two particle example, I didn't bring in any Fourier transform. I'm just saying I have two particles. I go to normal modes. It becomes two particle with some omega 1 and omega 2. This is some k. And then I convert it into a quantum problem of two oscillators. Do you follow this pattern? Okay.
So like what I'm confused is like if we ignore the interaction, like when we consider them as two independent harmonic oscillators, then we won't have an dispersion relation, right?
What do you mean by we won't have dispersion relation?
Like I think how we got the omega versus k relation was by considering two particles interaction, two adjacent particles interaction, and then assuming a traveling wave solution, and so we assumed that. So like when you write the Hamiltonian, like as in an n particle isolated Hamiltonian, like I can't understand how we would have traveling wave solutions anymore.
So can you write down this Hamiltonian in this form? Okay.
Yes,
So
sir.
follow. So now you do a Fourier transform. Now do you see how will you get these terms? Are you following?
No. So
Okay.
I'll read upon a reference book or something.
Yeah. Sorry, what did you say? I didn't follow.
I'll read up later in a reference book or something.
Yeah. So use these equations. Okay. Use these two equations at this step. Okay. You will get this in xk term. Okay, then you use the delta function identity, you will get that xk minus k term, and these two terms will not contribute in the delta function identity. Okay,
Okay.
so you asking that how do I get this equation from this equation, right? How do
Yes,
I
sir.
get this from this, right? So expand this equation. Actually, yes, you don't need normal mode. You just take this equation and do the Fourier transform is the normal mode transformation here. It's the same thing. So you just have to plug in that equation, this Fourier transform, and you get this form. So the purpose of Fourier transform is to take you to this isolated K space. Okay. Okay,
Okay.
but modulo that, is everything else clear?
Yes, sir.
Okay. So there is one more topic I wanted to do, but today I don't think I have time for that. This is this exchange force. But this is, so as I said, so you will encounter this kind of, this is one example, one very common routine example, that how do these phonons appear. I mean, these from your suggested, there are many more examples one can do, but I will not go into that. So just look up this from your suggested physics book or from Feynman's StatMech book. And then tomorrow I'll talk about the point of, we'll go to some examples in fermion, in many fermion, first two fermion and then many fermion. And one more point, there is a quiz tomorrow, which is usually our quizzes are Tuesday and Wednesday. And which chapter will be? It will be on the last week's lectures, which means many fermions and using the second quantization, etc. Okay, anything else?
Sir, I have a question about the mixed state, pure state thing.
Mixed state?
Like about like density matrices and mixed states, etc.
Yeah,
What-
pure state, mixed state. You have some questions on that.
Yes.
Okay, tell me.
Okay. So, like we know that suppose we have, let's say, a pure state of a superposition of, let's say, up and down versus a mixed state with 50% up and 50% down.
Right.
And the statistics, like when we do measurements and stuff, the statistics of the measurements will only remain same if the up and down are eigenvectors of the measurement we are taking, right? Because if we
Yes.
do some other measure, like we do some expectation value with some other operator, then
Yes.
the statistics will be different. Like for that question
Yeah.
that you're giving.
So you mean to say, so let's say I have a state like this. Okay. So up 1 by root 2 plus down z 1 by root 2, some psi. Okay. And another, this is an ensemble of psi. Another ensemble I have, let me call it psi tilde, which is 50% up. Right?
Yes.
So the only way you can distinguish them, if you do a z measurement, right? Because if a x measurement you do, they will give you the 50%.
If you do a Z measurement, it will give you 50%, 50%. Because these are sigmas up Z, down Z, right?
Yeah, right. So what measurement you should do to
You should do a
distinguish?
sigma X measurement, I think.
Yeah, correct. So because this is a x state.
So like the point is that
So unless you are doing an x measurement, you cannot
can't do-
distinguish. Correct.
So like if you do it on some other operator, if you do the expectation value on some other operator, we can have different statistics, which will
No.
help us distinguish these two.
No. So that is why this quiz question was there, right? So that means this, if Alice and Bob does a x measurement and they find perfect correlation or anti-correlation, then they know that that was an entangled pair.
And
There is
another,
no other combination is possible. So they have to somehow land on this, or they have to agree that I will do x. And if they accidentally choose z, then they cannot make out.
so they will not be able to differentiate between ensemble,
Yes.
mixed state, and partial. Okay,
Correct.
and another thing, like we say that it's entangled, like we say that in density matrix formalism that it's entangled if the trace of the reduced density operator square is less than 1, right? So
No,
the,
we said that's a mixed state.
yeah, sorry, less than
Yes.
1 is the mixed state.
Hmm.
So we say that the subsystem is a mixed state means entanglement.
Hmm.
Now,
For an entangled state, the subsystem is a mixed state. Correct.
but is this mixed state definition coming only from the fact that the trace of rho square is less than 1, or is there like some other physical intuition behind
No,
it?
you can also argue it physically without getting into the density matrix. So you take a mixed if you have only access to part of it. So if you see it from point of view of Alice, physical reason, right? So from Alice, we'll do some measurement in some basis. There is no way Alice can make out, right? It's a mixed state for Alice.
Yes.
So that physical fact is captured into density matrix.
The notion of a reduced density operator is that even for entangled state, we have some notion of an individual particle that Alice will have.
Yeah, so any multi-part system, the whole notion of reduced density matrix is I have a multi-part system and somehow I have access only to one part.
Correct.
And I have to integrate out the B part. Now, if the A and B are not entangled, then that integrating out is trivial. But if A and B are entangled, then that integrating out is non-trivial. And that gives you this mixed state form.
But if it is entangled, then
that is the point. If it is entangled, then when you integrate out the part B, then the reduced density matrix you get is a mixed state.
From Alice's point of view, it will be mixed. But from the whole point of view, it's still a pure state, right?
Sorry, say that again.
Like from Alice, if the particle that Alice has, that is a mixed state, right?
Yes, correct.
But the whole AB system is still
Yes,
pure.
but that information is not accessible to Alice, right?
Alice.
That is the whole point.
Okay. So yeah,
right?
if she thinks that her system is mixed, then she will know that it's entangled.
Yes, if she have information about the whole system, but she doesn't. That is the whole point. You are part for, and that is true for any experiment in the world, right? You have access to a system which is part of a bigger system.
So like the mixed state shows that there is some lack of knowledge. So that means there should be entanglement. Because unentangled, everybody has full knowledge of the system. Okay.
Yes. And that is that point of view leads to opens the door to a whole course, which we might do sometimes later in open quantum system, where you describe a quantum system as a mixed state always. And because a quantum system, so you treat the whole problem as you are doing anything as a part of a bigger system. Then you develop the whole formalism. So density matrix is useful to develop that formalism. And
there
that is
interaction with outside. Like
yeah,
outside
so then you see the equation of motion for that system is not Schrodinger equation. It's something called Lindblad or Redfield, some other kind of equation. Yeah, which will have a part which is coming from the influence of the other part which you don't know.
Okay.
Yeah, and this is also true in classical mechanics. When you do this Fokker-Planck or something, so you will do in advanced StatMech, you will see that. In a multi-part system, some unknown force is always doing something to the system. Then how to handle that?
Okay.
It's different technically, but idea is same. Yeah.
Yeah, and in assignment 2, one question you have mentioned that there are two ways to check whether it's entangled. Like one is this case of reduced density operator less than one thing, and the other one is just that the reduced density operator will be the same as the A state, right?
Yeah, wait, I have to remind myself what was the question, but I think it was what was the
Like
one was
the
the simple trace. One is using the trace formula. Okay. Another is I think something else. You have to do using the spins, writing it directly. Something of that.
In direct product form.
Yeah, I have to remind what was the second way I was thinking. What was the question and what was the second way?
No, you had said that by using density matrix, there are two ways to do it. One is the trace thing that we can do. That system is mixed. That is
yes.
Fine. See, now if they were not entangled, then the reduced density operator would be the same as the full density operator for A state, right? Will be the pure A state operator.
Yes, correct. If you are getting a pure state, a pure state form, but the way to check pure state is by the
trace thing. Yeah.
Trace. But there, what was the other way? I don't remember. I have to look at myself. When I wrote the question, I thought something which I don't remember now.
Yeah, you also said that you know two, three ways to understand if state is
What?
entangled or not. So I was also confused at that point.
What? Sorry, say that again. Yeah, two states are entangled or not. Of course, there are two ways to understand. One is by writing density matrix, taking partial trace. Another is by non-separability, right?
Yeah.
When you cannot write it in a product form.
Tensor.
These are the at least two ways. I don't know if I am thinking about this, that I have to
Yeah, yeah, at
look at the
least two ways
question.
you said.
These questions were created last year, so I don't remember what I thought that time. I'll give you the solution today, by the way. Yeah.
Yeah.
Anything else?
Sir, I had a question about the last day's lecture.
Okay.
You for the Fock space for fermions, I am not still under, and I cannot understand why the fermions are checking. Like my question is, if I put a particle in the second state, the particle in the sixth state is understanding there is a particle in two. That is, it is as you said that the number of occupancies are compromised, and so that's why there is a minus sign coming in front because there is a
Hmm.
particle at this lowest level. But why is
Hmm.
it not possible to think that the particle which is going to the lowest state, that is also seeing the particle which are higher in the higher states? So why the other way is not possible?
So you mean to say that why I am saying it in this way, that a particle in the, so how does the particle know, right? Is that sort
Yeah,
of thing?
yeah.
Yeah. Yeah.
No,
So this.
no, that's not. That is not my point. It actually says that the particle that goes to the lower state, that does not see the higher energy particle, but the particle that is on the
No,
higher state,
no,
that
that
is
is not
seeing
the
that
point.
there
I'm
is a
just saying,
particle.
if you want to put a particle, then you have to consider the existing configuration. That problem is not there in boson. That happens in fermion. That is the entire purpose of that statement. Right?
Yeah, but
That's the only thing I'm saying.
yeah, but configuration means that the number of particles that are occupied
Yes.
in the lower states. But why not
No,
the
any
higher
state.
state?
Any state. The fact that you put two particles in one state, that means you need to know where you can put it and where you cannot.
Okay.
So that
Then
that
why
means that,
only mine? Yeah. Sorry.
and there is a relative minus sign between these two. That is all I'm saying. That difference, that the existing configuration has a difference in terms of a minus sign. Now where you put the minus sign, that's arbitrary. But there is a minus sign difference between these two.
No, my point is like when we write the fermionic states, like Fk acting on something 1k, then
Yeah.
it is then it is 0k, and outside there is a normalization of minus 1 to the power sum over all the particles below the states.
Hmm.
So it is checking the configuration below, then seeing that where it can occupy a state, and then it's deciding it will be a minus sign or plus sign. But why it
Yes.
is not true that it is also seeing the particles which are above it, and also checking the occupancy where according to
No,
that, and then
you can also do the above, but you have to choose one of the two.
okay,
That's all
so
I'm.
it is just a formalism where we are
Yeah.
saying that the only the particles which are sitting
Yeah.
lower, those will be considered and
It is just
not
a
higher.
way to keep track of that sign. It's just a
Okay,
setup for
okay,
that. And it's an arbitrary choice, but once you make that choice, you have to stick to it for a given calculation.
okay, okay.
That is all. The
Yeah,
fact that when you flip two particles, then there is a minus sign. You have to
mm,
account for it systematically somewhere. And that account is this.
okay.
Okay?
And for there is a question from the partial trace thing that
Hmm.
you there you asked to write the density matrix. I mean, you
Hmm.
wrote that, but asked us to check. There is a problem in getting the direct product of two by two matrices. Like we
Okay.
multiply one,
Yeah.
like
So
if
I
I have,
told it in the class, right? If I have A12, A21, A22,
yeah,
how to
A11
take
will
that?
be multiplied with the B11, four B11 terms, and that will make a 2 by 2 block, and the whole thing will be 4 by 4.
Yes.
Yeah, but
Right.
the density matrix is not matching with the thing you wrote. I mean,
What? I didn't follow.
if I evaluate the density matrix, that is not matching with the thing you wrote in the class. So is it okay if I send you the picture?
Yeah, yeah, sure.
Yeah,
Send me Piazza or something. I'll take
yeah,
a
okay,
look at what wrong and
okay,
what exactly are you talking
okay.
about.
And all the row square will be equal to row or less than row
Rho
for
square is
mixed
equal to rho for pure states.
pure states. But
Yes.
row will trace of row will be always one, right? For mixed state or
Trace of
pure
rho will
state.
be always one, but what will be the trace of rho square? That is
Yeah,
the
yeah,
distinct.
yeah, yeah. Okay.
Yeah.
But for partial trace, the trace of row will not be one. So in that case, we can say that
No,
that is a
partial
part
trace,
of.
the trace of rho. No, no, no. Why? Partial trace will be also one.
Okay. Okay, 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 okay. Yeah, yeah.
Trace of rho is always one. Trace of
Always
rho
one.
square
Yeah,
is the indicator.
yeah. Okay. So in your
Because
assignment
even a
two,
partial row, that is also a state. The trace of row is one is indicated that sum of probability is one. That is never
yeah,
violated.
yeah, yeah. So actually, you wrote something that how to say something about from the density matrix. So I thought there must be anything
The
you
density
can.
matrix, there are two things you can do. You have to calculate
Yeah,
the row square, and then
the
you see
row
row square
square.
is
Yeah,
equal to
trace. Yeah,
or the trace is less than one or
yeah,
not. These are
yeah,
the
yeah,
two
yeah,
indicators.
yeah, yeah.
This is an algorithmic way to do this when you are doing some messy, complicated. But there is a
Yeah,
physical way also, which is the other way. So every
yeah.
equation you write, there is a language and a physical word behind it. So this is generally true for the whole physics, any physics course.
Yeah, okay.
We
And
convert it into an algorithmic way because sometimes we want to put it in a computer, calculate it blindly without depending on every time. If you have to describe it, then it becomes you cannot proceed with the calculation. That's why you are trying to make it algorithmic.
okay.
Yeah.
And I have a question from gauge transformation. So can I say
Okay.
it now? Yeah.
Yeah. Let me know.
So yeah, my question is usually before taking into account the fields or so, we say that we are introducing psi prime, which is e to the power I alpha and psi. Then if we plug it into the Schrodinger equation, we can see that there is some discrepancy which can be taken into account by introducing the fields.
Hmm.
So that alpha is basically I lambda by h cross. Okay.
Not necessarily. The alpha can be anything.
No, actually, my problem is, I mean, when we put that into the Schrodinger equation, then and try to get like uh, to equate the LHS and RHS, that I need to get that grad minus IQA square thing to check if the two things are.
Alpha has to be a dimensionless quantity. That is the only
Yeah,
thing I am saying. Because it's a
yeah,
to the power. So that
yeah,
alpha can be anything, right?
yeah.
So
And
it
how
need
is
not
it
be.
coming with
If you try
A?
to give it an H bar form, then
Yeah,
you have to care about lot of things. You can do it, but it has to be. For example, when I do dynamics, right? IH to the power I P by H bar T. So then this dimension need to be taken care of. This whole object has to be inverse time, such that it's a dimensionless factor.
yeah, yeah.
So you cannot
But
put each randomly unless you take care of the dimension. You can do that. If you want, you can do that, but it's not essential.
then how is it appearing in the expression of Schrodinger equation? Like, what factor is going to come with A? Because there is H cross, right?
What is A? What is A?
A means the vector potential. We write I H cross grad minus E into A, that square, minus Q into phi, where A and phi are the vector and scalar potentials of EM
Yeah,
field.
you have to do everything in a way such that this whole object has dimension of E, right?
Yeah.
So that you have to be careful about. So maybe, so
Okay.
I have to check the expressions exactly myself. I don't have it with me right now. But
Yeah, okay.
every term has to maintain this energy dimension.
Okay.
For that, you might have to put h bar here, but I don't think it's needed. The way I have written, it has the energy because this h has so vector potential has the same dimension as potential.
Okay.
So it should appear in that way. It should appear on its own.
Yeah. And the or Q or something, those Q or alpha, everything will come in such a way that ultimately that is turning out to be an energy expression.
Yeah, that is how it should come.
Okay. Are we going to have office hours tomorrow?
Yeah, we can have office hour tomorrow actually. So if you want, just let me know in Piazza, then I'll log in.
Okay.
Okay.
Sure. Yeah. Yeah. Thank you,
Okay.
sir.
Yeah, that's all. Yeah, you can.